Hello viewers. So in this video, I'm going to teach you how to derive the formula for the effective spring constant for the two types of springs we have. So we have springs that are connected in series as shown in this first diagram here. We have this spring and this spring. These two are connected in series. And then we have another type which is springs connected parallel to each other. So we have this diagram is showing springs connected parallel to each other. And we also have the other diagram here which is also showing the same type of springs which are in parallel. So this is also showing parallel because if you use this mass to compress this spring here, the other spring is going to be straight. And if you use this mass to stretch this spring here, the other spring is going to be compressed. So if you see this type of diagram, this is parallel. And if you see this type of diagram, it means we have a series type of spring. So let's see how we can drive their formulas. So we'll start with the series one, then we'll go to the parallel ones. Now for springs connected in series, getting it from Hooke's law that says the force is equal to K multiplied by the displacement, where K is the spring constant, X is the displacement, then F is the restoring force. Their displacements. Let's say we have this one is spring one. So let's call this one spring number one and call this one spring number two. So we have two springs here connected in series. So their displacement, getting it from here, the displacement will be equal to, now displacement for spring number one will be equal to the force divided by the spring constant. So we also call it spring constant number one. So we have the displacement for the first spring, and that will come with the spring constant for it. Then the displacement for the second one, we'll call it x2, will be equal to the force divided by K2. Now remember, the force will still be the same. The restoring force will still be the same since these have got a single path. The restoring force will still be the same. So we'll have x1 is equal to F over K1 and x2 is equal to F over K2. Now, the total displacement, which we'll call the effective displacement, displacement total or effective displacement will be equal to F over KEF, let's call it effective spring constant. So this is what we have here. Our X total will be equal to force divided by the effective spring constant. Now what we are looking for is the formula that can help us find this effective spring constant. So let's continue. We'll say, therefore, the total will be equal to x1, the total displacement will be equal to displacement number one added to displacement number two, like that. Then when we replace, we find that on x total, we'll replace with that. We are going to have our force divided by the effective spring constant. This will be equal to, our x1 is F over K1, then added to our x2 is F over K2. So this will be our step. Then from there, we can still say, here we have F over K1 added to F over K2. We can factor out F since F is common here and there. So we'll say what we have is F over K EF, which is effective spring constant, is equal to, we'll have our F factored out, we'll say F over 1. Then Inside here, what will remain is 1 over K1 added to 1 over K2, like that. So 1 over K1 added to 1 over K2. Let's hope you are able to see that. This is K2. Then after that, what we are going to do is, since we don't want this force here, we want to get rid of it, we're going to multiply the whole thing, this side and that side, the whole thing, we're going to multiply it by 1 over F. When we do that, you find that this F and that F will go with that F there. What will remain is we'll have 1 over KEF, which is the effective spring constant, will be equal to what is remaining there will be 1 over K1 added to 1 over K2. We are able to see that. So this is what is remaining here. When we reach this stage, we'll continue. We'll say, on the other page, we found that 1 over KEF is equal to 1 over K1 added to 1 over K2. That's what we have. So for now, let's work out what is on the right side here. We find the common denominator. This is K1 multiplied by K2. So we'll say K1 by K2. That's our common denominator. Then K1 will go once here, or we'll go K1 here, leaving K2. So we'll have K2, then added to K2 will go K2 here, leaving K1. So we'll say added to K1. Then we can now bring our 1 over KEF there, which is the effective spring constant. When you cross multiply, you find that we are going to have KEF is equal to, sorry for that, we're going to have KEF multiplied by that, which is K2 added to K1, will be equal to K1, K2 multiplied by 1 will give us K1 multiplied by K2. Then, since we are looking for the effective spring constant, we're going to divide by K2 plus K1 here and there. When we do that, what we'll get is our KEF, which is our effective spring constant, will be equal to K1, K2 divided by K2 plus K1. So this is the formula that we can use to find the effective spring constant. If you are using springs that are connected either in series, yes, just in series, not parallel. So this is the formula used to find the effective spring constant for springs connected in series. You can have more than 2. So if you have more than 2, your formula will basically be, there will be just an increase. If you have more than 2, for example, you have 3, it will be K1, K2 multiplied by K3 over K2 plus K1 plus K3. So yeah, this is the formula you need for that. So for the series one, it's done. We can leave it like that. We'll go to the parallel ones. How do we find the formula that can help us find the effective spring constant for springs connected parallel to each other? This is how you do it. So we'll say again on the other side, getting it from here, our force is equal to K multiplied by X. So now the force will be equal to K multiplied by X. If we have 2 springs, the force for the first spring will be equal to K1 multiplied by X. In this case, the displacement will be the same, but the force will differ. So F1 will be equal to K1 multiplied by the displacement. Then F2 will be equal to K2 multiplied by the displacement. Then force, the total force, which we'll call Ft, or let's write the total, will be equal to Kx, where this is the effective spring constant multiplied by x. Let me write that properly. So we'll have K effective multiplied by the displacement. So this will be our total. Our F1 will be equal to K1x, our F2 will be equal to K2x, and our F total will be equal to K effective multiplied by that. When we bring this together, what we are going to have is um, F total. Remember, this will be equal to F1 added to F2, like that. Then when we replace here, we'll have our K effective multiplied by X will be equal to K1 2 multiplied by X added to K2 2 multiplied by X. Our KEF multiplied by X will be equal to, since X is common here, we can factor it out. We'll say we have K1 added to K2, then multiplied by X there. What we do after this is we're going to divide by X, or rather we'll say we're multiplying the whole equation by X. Then we'll say this and that will go, and that will also go. What we'll have is KEF, which is the effective spring constant, will be equal to K1 added to K2. So this is the formula you use to find the effective spring constant for springs connected parallel to each other. So K effective, or KEFF, meaning the effective or the total spring constant, will be equal to K1 added to K2. If you have more than 2 springs, it will be added to K3, and it can keep on going like that. So this is how you derive the formulas for those 2 types of springs, one in series and the other in parallel. If you found this video interesting and helpful, don't forget to subscribe to our channel, like and comment, so that as we post also new content, don't forget to turn on the bell so that you'll be notified to say there's some new content you need to check out, and you'll be able to move together with us.